So we've been looking at how to analyze patterns and different ways to measure patterns or display patterns. But this is also sort of leading us toward a conversation about statistical control, where we start finding that when we add in additional variables into our analyses, we can find slightly different things happening. And so I want to kind of run through what we're thinking about when we talk about statistical control and sort of try to visualize what's actually happening with this. So I'm going to begin that conversation by returning us to our discussion from way back about how do we establish causality. And so there were four things that I sort of put forward as sort of saying, these are things that must be in place if we're going to make a plausible argument about causality. One of those is that there has to be an association, a pattern. You should be able to look at your table or you should be able to look at your graph and say, aha, I see it, there it is. There's a relationship of some kind between these variables, or there's a difference between these categories. So that's a necessary piece. You have to have that, we think. Secondly, we have the time order that cause must not precede effect. Again, we think there's messiness around this, but typically if we're going to make causal arguments, we should be able to at least say this happened and then that happened. A third piece is that we should be able to tell a coherent story. We should have a causal mechanism that links these two things together, that they're not just sort of random bits of data that happen to be correlated, but we can actually sort of anticipate that there might be and tell a story about why that would be. And then the fourth piece that has to be in place, and this is really the tricky piece, is we need to demonstrate that our pattern is not spurious, that it's not just sort of a mistake or a fluke or the result of something else that we didn't anticipate. And that means ruling out alternative explanations that might account for this pattern. And so in an experimental sense, we do that by randomly assigning cases to groups and then applying a treatment. And we sort of use a random assignment to say these groups are identical. Therefore, if there's a difference between our treatment and control group, there must be a difference in the overall, in the way the world works, and it's not a spurious relationship. Alternatively, we can use the comparative method, right, where we carefully select two cases that are basically identical, but they have a difference on one dimension, and then we see a difference somewhere else. And we'd say, I bet those things are causally related because I've selected cases that are otherwise identical. But in a statistical context, we're often just picking large amounts of observational data. I sampled 1,000 people, or I went through the historical record and I found 300 conflicts that were assembling data from the world, and that data is not going to be identical. Like those cases are going to have differences. They're going to have lots of differences. It's not the comparative method. And I don't have control over how those cases were created or who got assigned what treatment because I'm just grabbing this data from the world. I'm not in an experimental setting. And so in order to establish non-spuriousness, I, the researcher, need to consider alternative explanations for what might be driving these patterns. And I, the researcher, need to be able to show that it's not something else. And so observational data is really tricky to work with in terms of establishing non-spuriousness, right? We're collecting it from the real world. It's not that experimental data. But what that's a good thing, right? I want to disparage observational data and statistical analysis because what it's giving us is data that has strong external validity. We know that what we are observing in our sample and our study is data that exists in the world, that it's real, it's reasonable. Whereas in an experimental setting, oftentimes laboratory settings are unusual. Will people behave the same way in a laboratory setting where you're sort of controlling things versus the actual real world? And we don't necessarily know that. Experimental designs oftentimes struggle to make that case of external validity, that this will work out there in the larger world. But nailing down non-spuriousness in a statistical sense with observational data is really tricky because we as people rarely understand the full complexity of what's involved in the data that we're working with and the patterns and how these things interrelate. And so it oftentimes requires a great deal of thought and scrutiny to be able to do this well. I want to give some examples of what I mean when I talk about control in a statistical sense. And so this is Data that was collected as part of a survey that a group I'm involved in with the Research Institute in Autonomous Systems did. It's a national survey that asked people about their attitudes toward autonomous systems, basically drones, in a wide variety of contexts, right? So use for drones in research, use for drones in surveillance of borders, use for drones in um, delivering life vests to drowning victims, right? In the lots of contexts. And then people were asked if they are worried about um, abuse of privacy and safety by governments or by private companies, or they could say they're not worried at all with either, or they could say, yeah, I'm worried about that with both. Um, and so we can sort of look at the overall sort of number and find that, a lot of people say that they are worried. Nearly half of our sample said that they were very worried. But we could also ask, well, is there a gendered gap? Is there a difference between men and women how they think about these issues of safety? And so I am separating out my data in the table below by gender. Right? So I am, one could say, controlling for gender. I'm creating these sort of this situation where I can look at people and look just at men and see that only 213 or about 10% of men said that they were not worried about either, but nearly 50% said they were very worried about both. And so I can sort of look at that and say, well, that's how men behave, and I've controlled for that. And if I find the exact same pattern when I look, or basically statistically this similar pattern, when I look at women, I can say gender's not driving this pattern. They're not related, they're not linked. But instead, what I find is that when I look at the row for women, I find that, well, there's slightly more women in our sample than men, and slightly more women say not worried about either. About Well, the place where we see the biggest difference is with very worried about both, where women are more likely to say very worried about both. And so based on that initial pattern, I could maybe put forward a claim that women are more concerned about drones than men. And that's true if we're just looking at what are the patterns that I found in my data. And if I'm just simply saying this is the pattern, that might be okay. But if I'm going to try and make some argument that this is somehow related to gender, and I'm trying to explain, well, it's because women something something, or because men something something, once I start making sort of a causal claim about that, I run up against this problem of, well, is that spurious? Is it more than just women versus men and there's a difference? Is it something else that I'm not seeing? And one thing that I might speculate on is that as people get older, they become more skeptical of new technology. That young people are more easily adaptable to new technology, and old people are more likely to find technology terrifying. I think that's a reasonable conjecture. I haven't tested that or proved that yet, but I think that's a reasonable story to tell. And then I would say, well, but men and women both get older, so maybe that's not a problem. And then I realized, wait a second, men tend to die off a lot sooner than women. And so it might be that that difference I'm seeing is just a function of women being an older population than men, because women tend to live longer. And so I have more of those women who are older in age in my survey than I have men. And so I need to figure out and control for, is it just gender or is it age? What's going on here? And so what I'm doing to do this in a way that I think is visually possible is I did sort of an interesting data visualization thing. I separated my men row and my women row out into a table of men and a table of women, in which I added a dimension of age. So now I have, I'm looking at three variables. I'm looking at that sort of are you worried variable. I'm looking at age, and I'm looking at gender. And because I've got, I don't know, what is that, 4 columns and 6 rows, that's 24 cells that compare across 2 tables. That's really messy. So I took an extra step and used Excel's conditional formatting to highlight cases where you're below the average and make them green, and cases where you're above the average and make them red. And that allows me to sort of look at this pattern. And so what I see is, if I'm looking at my table for men, that sure enough, young men tend to be less worried, And the place where we see the most concern is with older men. That group, right, seems to be the most concerned about autonomous systems and drones. And so that would fit with the idea that as we get older, we get more resistant to technology. But when I jump down to the women table, what I find is that 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 column on the right is all way above the average, with people expressing more concern in that category, and that's true regardless of age. That women in the 18 to 24 range are much more likely to say, "I'm very worried about this," than they are to say, "Not worried about either." And so, what I conclude from that is that yes, it does seem that as we get older, we become more worried about technology. That pattern is there. But even controlling for that, even separating out ages, I still see women being more skeptical or more concerned about drones than men. And so I can say I've essentially controlled for that relationship. I have ruled it out as a potential, ruled out age as a potential alternate explanation for the pattern that I'm seeing. And I can say, while there might be other things out there that would make that pattern between men and women spurious, it's not age. I've controlled for age. I've sort of checked the box and said that's not what's driving this pattern. So when we talk about statistical control, particularly in a regression context, that's essentially what we're saying. We're saying that I've analyzed subgroups of my data, separating out things on different dimensions to be able to say that's not really what's driving this. The pattern persists, holds up, and remains even when I separate things out. Now I can do that with tables fairly easily because categorical data can be sort of, organized into tables, and I can break my tables out and drill down into what's happening in individual rows, and I can get creative with my data visualization. I can sort of do this by separating things out. But when we're working with continuous data, that doesn't work quite as well. It gets really messy, and it requires increasingly more cases to be able to tell the story in a coherent way. And so we oftentimes do a slightly different strategy for control in a regression context, not where we're trying to separate things out, but we're actually trying to push things together. We're trying to find the differences that come with men versus women, or with each of these age categories. We figure out what those differences are on average. We record those differences on average, and then we try to adjust our data to sort of take those differences into account, so we can talk about a single pattern that we can then analyze and describe. And I've got a video that kind of helps illustrate this, and we're going to come back to regression and talk about this in greater detail in the future. But for right now, I want to kind of get at this idea that what we're doing with regression is we're taking things that are different. We are figuring out what those differences are in terms of the averages on X here and the averages on Y. We are recording that, so we're going to use that later when we talk about these patterns. But once we've sort of figured out what those differences are, we're going to collapse them together and say, I've dealt with that difference, and now what is the pattern that remains after that difference has been taken care of? And so the visual I'm going to show you is an example that might look like Simpson's paradox, which we'll talk about at a later date, where I have two different groups. And if I was going to try and maybe think about what the overall pattern is, I would say that it's probably a positive relationship where I can kind of go up and to the right. But in fact, each of those groups is sort of distinct. The sort of W group, the orange group, is sort of higher on average. The other group, the 0W group, the black dots, which are lower on average. And so once I control for that, what I find is that the pattern is actually sort of negative. And so I'll try to play this video in a way that kind of illustrates what we'll be trying to do when we think about regression. So it's identifying the overall averages for X. It's identifying the overall averages for Y. It's taking those into account. It's going to calculate a slope for those, which we'll be able to use to be able to unpack those things later when we want. And what we find is that at the end of that, there's a single relationship, and it's actually a negative relationship once you control for the differences in X and Y. And so what we'll be doing a lot when we talk about statistics and statistical control is trying to use some of the tools of math to try to isolate differences, so we can talk about what the pattern is conditional on or controlling for this other piece that we've taken out, that we've isolated, that we've sort of separated out and concluded this is or is not part of that story.